So today, what I'm planning to do is I'm going to go over 3 questions. So if you guys attended the previous sessions, we had 3 more sessions before. I tried to solve 6 problems, so 2 per session. So let's see, I will do my best to solve 3 questions today. So the way I'm gonna do is you don't need any code, anything now. So if you have, I don't know, so your Jupyter notebook or any IDE, you can run Python code. If you don't have anything installed in your computer, you can just open Google Colab. So Google Colab, okay, you can simply open it and then code with me. So the way I'm going to solve these problems is, again, in the interviews, you are going to be asked, these are interview questions, you're going to be asked questions from fundamentals of probability. So in a data science interview, especially I'm talking about big companies, they may not expect the whole solution from you. They may maybe want to see how you are approaching the question or the problem. And sometimes, of course, the full solution. So they may help you, give you some hints. So what I'm going to do today is I'm going to do 2 things. One is try my best to solve the problem mathematically. And also, again, try my best to solve the problem using simulation, so coding. So sometimes they may ask you to solve the problem using coding. And that happens frequently. So I think we should be familiar with how we can solve probability or stat problems using coding. So the 9th question, if you see, 9th question is about an A/B test. Again, you may not solve the whole A/B test problem in an interview, but you should have a very good understanding of each component of the A/B test. So I'll try my best to go over those steps and then get the solution together with you guys. So the first 2 problems sound very simple, but let's see. And again, doing live coding is always risky. So if anything doesn't work, so just I mean, forgive me, okay? Okay, let's get started with the first one. Let's imagine that we have 600 cards. This number doesn't have to be 600, okay? So it can be 1,000 or 400. So that's why we are going to do a simulation and see how we can solve this problem. So let's say we have 600 cards, and these cards are numbered from 1 to 600, okay? 1, 2, 3, 4, 5. And then we shuffle the cards. That means the cards are not coming in a specific order, so it's a random order. And then we pick 3 cards randomly. So at this time, you can ask me, are we going to pick the cards with or without replacement? And I think the solution is going to be different when you pick the cards with or without replacement. For now, let's assume that we are picking the cards without replacement, and then we can solve this problem in 2 ways. With simulation, I'm going to try my best to solve the problem mathematically too. But again, let's see. So we are going to pick cards randomly, one at a time. And again, either with replacement or without replacement. So the question is, what is the probability of each subsequent card being larger than the previous drawn card? So let's say you draw 3 cards, X1, X2, and X3. So what is the probability that each subsequent card is being larger than the previous drawn? In other words, what is the probability that X3 is greater than X2 and X2 is greater than X1? So that is the problem. Okay, this is the problem that we want to solve. And I'm just now thinking how we can solve this problem. So should we start with simulation first? I think simulation is going to be simpler. Let's understand with simulation how the solution looks like, or what the result looks like. And then from there, let's try to solve it mathematically and then see if our mathematical solution is matching with the simulation. Okay, so let's get started. First of all, I'm going to let me move this guy over here. And by the way, you can ask your questions using Q&A or chat, but I prefer receiving questions through Q&A because chat, I mean, I may lose the question. So many messages already posted there. Okay, so first of all, let's import the required, libraries. So let me import random. maybe I'm going to use random. I think I'm going to use random for picking a card randomly. So that's why I imported random. And then let me also import NumPy as NP. Okay, so these are the two, libraries that I'm going to use for this problem. Okay, so now let's think. Let us create 600 numbers, each number representing one card. So for that, I will call this cards, okay? And then it's a range of numbers, right? From 1 to 601, right? So now I have cards from 1 to 600. So let's check the length of the cards. So I have 600 numbers. Again, each number is representing cards. We can also check cards, first numbers. So 1, 2, 3, 4, 5, 6, 10. So these are the numbers representing different cards. Now, you can shuffle the cards. It's not going to change what I'm going to do next. So in the question, it says shuffle. So you can shuffle the card, or without shuffling, it's not going to, because we are going to randomly pick 3 cards from this deck. Can we get the download link for the notebook post the session? So what I can do for you is after this session, so we can find a way to share this notebook with you. For that, I need to talk with my friends from Magnimind. So that we can do. Is this notebook shape? So the second question also the same. So there is no notebook here because, again, they are just doing everything from scratch. I can just post this question. I can just copy and post this question from the chat. So you can have the question, okay? Here. All right. Or you can quickly type the question yourself. Again, there is nothing required here. We're just going to do the coding from scratch together. Okay, so let me continue. We created cards from 1 to 600. The next thing is, what I'm going to do is I'm going to repeat an experiment. What is this experiment? Each time, at each experiment, I'm going to pick 3 cards, and I'm going to check if the numbers in the cards, and then if and I'm going to see if the last card is greater than the second card, and the second card is greater than the first card. So that's what I'm going to do. So, and then if I get the case where third is greater than the second is greater than the first, so that is satisfying this condition. So in other words, I'm going to repeat a number of experiments, and then I'm going to count how many times my experiment is satisfying this condition. That's what I'm going to do. Okay. So the number of times satisfying this condition, let me hold that with the variable j. Okay. Okay. J is 0. At first, there is no experiment, right? Satisfying a condition. J is 0. And let me repeat this experiment, I don't know, 100,000 times. Okay. So you can start from 1,000 times to 1,000. It's not going to change the result that significantly. All right. So first, I'm going to do this simulation for the case where we are going to pick the card without replacement. In other words, I'm going to pick the first card, and we have 599 cards left, right, in the deck. And then I'm going to pick the second card. Now we have 598 cards. So this is going to be different than I pick one card and put it back, right? So picking sampling with replacement. Okay, so again, I'm just going to repeat this experiment as many as number of n, right? So range of n. Okay. So what I'm going to do is I'm going to copy my array cards. So again, please do not just ignore all the inefficiencies in the code. I just want to solve this problem as explicit as possible. So you can do the coding in much better way, in a more efficient way, which is nice. But for now, please just ignore any inefficiency in the code. So I'm just going to copy my array so that I'm going to make this change. So when I pick a card, I'm going to remove that card from my cards. Okay, so that will happen for cards to array. So cards array is going to be remaining unchanged, because I'm going to use the same set of cards for each experiment. But within the experiment, as I remove one card, I'm going to remove that from cards 2 array. So that's why I'm copying cards array into cards 2 array. Okay. So now I have 600 cards in my hand. Let me pick my first card. Okay. So from my cards 2, I'm going to pick a random card. So from random library, okay, I'm going to use choice. Basically, choice is going to pick a random, see, random dot choice. It's going to pick a random number, okay, from these 10 numbers. All right, it picks 7. If you run this again, it's going to be a different number. Most likely going to be a different number. So we pick the first number, okay. After we pick the first number, let me update my cards 2 array, because the first card, which is X1, right now I don't know what card is that. It's removed from the deck of the cards. So let me remove it. So let me update cards 2. This is a NumPy array. Again, you can do this in many different ways. I'm just going to delete from this NumPy array a specific number. What is that specific number? From my cards 2 array, I'm going to delete the element with this index, where cards 2 is X2. Okay, so let me tell you what is happening here. So let's say A is this. Okay, A is this. What is A? A is 8. All right. Now I'm going to see where A is located. So NumPy where, okay, cards A. So if I do this, it's going to give me the index of this number, okay, whatever that number is, index of, and then if I say A, okay, A of this. Cards is A. So okay, so this is going. Let me skip this one. This is giving me where the cards array has this specific A. So this is gonna give me the index of this number X2, and I'm going to delete the number in that index from this cards 2. That's what I'm doing here. Okay, I just wanted to show you what's happening here, but I think I just had some error here. Okay, let me continue without wasting any time. Now I'm going to pick another number. I'm going to repeat this 2 times. Okay, let me repeat this 2 times. Actually, I'm going to randomly pick a number 3 times. So this is going to be X2. Again, I am going to update cards 2. Okay, so this is X1. This is X2. And then I'm going to pick my 3rd number. All right. So this is going to be the 3rd number. Okay, I picked all my 3 numbers. Now I'm going to just check the condition. Okay, if okay, X3 is greater than X2 and is greater than X1. Okay, I'm just going to increase the number of J. Okay, increment J. So if that is the case, so J is going to be incremented by 1, but it should be. Okay, now let's print J. Okay, let's see what is the error here. X1 is this, and cars 2 is NP delete cars 2, NP where cars 2 is X1, and I need to put one more. Yeah. Okay. Okay, so this is the probability where when I pick 3 numbers without replacement from 600 cards, the probability that the third card is going to be greater than second card, and second card is going to be greater than the first card. So it's a very simple simulation. We just got the answer. So we can repeat the same procedure for with replacement. Should cars, yeah. So I just fixed the error. Yeah, thank you. So let us do the just so that should be. I had an error earlier, so I just saw what the mistake is. So let us repeat the same procedure. I'm just going to copy this and post in here. But this time I'm not going to delete. Okay, I'm not going to delete the cards that I picked. In other words, I am replicating the same experiment, this time with replacement. Okay, with replacement, and then see if it's going to give me any different value. So as you see, the numbers are so close to each other. Now this may make us think that, oh, with or without replacement is giving me the same answer. So let us check if that is the case. So we tested this for 600 cards. Let's change the card number, I don't know, to 59. Okay, let's reduce the number of cards. Okay, let's reduce the number of cards and then see if these both cases are giving us the same result. So as you see, the 2 cases are actually giving us different results. So this is going to make us think why, when card number is big, these numbers are getting close to each other. When card number is small, these numbers are becoming a little bit different than each other. So let's explore this. I think if we solve this problem mathematically, that is going to give us, maybe the answer. But here, there are 2 solutions and they are giving very similar results. When card number is large, they are almost giving the same result. And what it is saying is with or without replacement for large number of cards is not going to make too much of a difference. Okay, now let's think about how we can solve this problem without coding. And then what we're going to find a solution, I'm going to write the code for that too. Okay, so let's see. Let's think a little bit about this and then should that be square brackets? Yeah, Jeffrey. Yeah, Jeffrey, hi, thank you. Yeah. Okay, thank you for the corrections. Okay, now let's think about how we can solve this problem mathematically. What I'm going to do is I'm going to demonstrate my thinking process with only 5 cards, okay? And then from there, maybe we can generalize the solution for many cards. Let's say I have 5 cards, okay? So let me only focus, when I pick 3 cards from 5 cards, let me only focus the cases where the first card is smaller than the second one is smaller than the third one. So if I can quantify the number of times that this case is going to occur, what is that case? The first card is smaller than the second card is smaller than the third one. If I can count these cases, then I can divide this number of satisfied cases by number of all different cases. So that number of all different cases will be different with or without replacement, right? So again, if you pick 3 cards from 5, okay, with replacements, how many different card combinations can you get? It's a very simple question. So if you pick 3 cards from 5 cards with replacements, okay, how many different 3 card combinations can you get? Right. So with replacement means if you pick the first card 1, you put the first card back into deck. So then the second card can be 1 as well. Even the third card can be 1 as well, right? So in that case, the number of different combinations is the first card can take any value from 1 to 5. The second card can take any value from 1 to 5. And the third card can take any value from 1 to 5. See, the number of total combinations is different when you sample with or without replacement. So let's do the same thing, a similar thing this time. When you pick 3 cards from with replacement, without replacement. Okay, without replacement. How many different card combinations can you get? Again, the first card can take any value from 1 to 5. But once you get the first card, there are only 4 cards available. The second case, the second card has only 4 possibilities, and the third card has only 3 possibilities. As you see, total number of possibilities is different. Okay, so for these two cases. All right, then what about the cases where the first card is less than the second card, the less than the third card? So do you think the total number of cases for x1 less than x2 less than x3, is it going to change for sampling with replacement or without replacement? So let me see. Can you tell me, hi Mary. So probably my friends are going to give you the link for posting a review, right? Thank you. So how can you, okay, x1 less than x2 less than x3, this is the condition that we're looking for. Do you think the number of cases where satisfying this condition, is it gonna change if we pick cards with replacement or without replacement? So Rupa says yes. Let's think about it. Do you think, I'm not talking about total number of cases. I'm talking about these specific cases where x1 is less than x2, less than x3. Do you think the number of cases where x1 is less than x2, less than x3 is going to change or what? With replacement and without replacement, I think the numbers are going to be different, right? I think the numbers are going to be different. What do you think? Because with replacement, so we might have the case where, let's say the first number is okay, let's think a little bit more carefully. Let's think a little bit carefully. Is it going to change or what? So again, with replacement, the only thing happening differently is you can pick the same card again. So is it going to, if any of these cards are coming the same, then we are not going to have this condition satisfied, right? So to have this condition satisfied, all 3 cards have to be different, right? In that case, with or without replacement, number of these cases, the cases satisfying this condition should not change, right? So again, that's how I'm thinking. Let me know if you think differently. But again, for this condition to satisfy, all 3 numbers have to be different. So with or without replacements, they have to be different. And yeah, so they can be smaller, bigger than each other. Hence, the number will change. Okay, let's think about this. Let's think about this. Okay. Let's continue. Let's continue. What I'm going to do next is I'm going to use these 5 cards. And Rupa, I'm going to come back to what you just said. I'm going to use 5 cards, and then let's see if we can enumerate number of times this x1 less than x2 less than x3 is satisfied for the case where we sample the cards without replacement. Okay. All right. So there are 5 cards. Let's say the first card is 1. The first card that we pick is 1. All right. Then how many? If the second card that we pick is 2, so x1 is less than x2, right? X1 is less than x2. Then the third card can be 3, okay, or 1, 2. The third card can be 4, or 1, 2. The third card can be 5. So I just started with the smaller value 1, and if the second number is 2, then I have 3 different cases where x1 less than x2 less than x3 is satisfied. All right, let's continue this thought process. If the first number is 2, then I can have, what is it? oh, by the way, so I can have 1, 2, 3. So I have more cases here, right? So I can have 1, then 3, right? Then 4, and then 1, then 3, then 5, and then I can have 1, then 4, then 5. Okay. So these are the total number of cases where the first number is 1. So if the first number is 2, then I have this following cases, 2, and then the second number is supposed to be 3, right? And 4, and then 2, 3, and 5. Okay, only 2 cases. Is there any other case where, oh, and then 2, 4, and 5. Okay, very good. So, and then you can continue this thought process, 3, and then what is it, 4 and 5, and then here we stop. Okay, simply using this example, can we come up with a mathematical equation which is going to give us total number of cases which satisfies x1 less than x2 less than x3 for any number of cards? So first of all, let us try to come up with a mathematical equation for this case. Okay, when the first number is 1, okay, I have 3 cases which starts with 2, and 2 cases which starts with 3, and 1 case which starts with 4. So let me use some mathematical expressions for it. If n is representing the number of cards, right? Number of cards. Then for the cases which begin with 1, I have n minus 2 cases. For the cases which begin with, so this is for 1 and 2, right? For the cases where I begin with 1, and let me write this way. Please be patient. I'm just going to come up with the equation, and then we are going to code the equation and then move to the next question. Again, question sounds very simple, but we need to be a little bit patient to understand what really is actually going on. So for the cases where I have 1 and 2, I have n number of 2 cases, right? 1, 2, 3, 1, 2, 4, 1, 2, 5. There are n number of 2 cases. For the cases where I have 1 and 3, the first 2 numbers. So I started from reverse. Okay, I started from reverse means I am looking at the third numbers. When I have the first 2 numbers, 1 and 3, then I have how many? N number, n minus, what is it? 3, right? And n minus 3 cases. When the first 2 numbers are 1 and 4, okay, then I have n minus 4 cases. Again, n is in this case number of cards when it is 5. So I almost got some connection right here between n and what the first number is and what the second number is. If the difference between the first and the second number is 1, I have n minus 2 cases. If the difference between first number and the second number is 2, I have n minus 3 cases. If the difference between first number and the second number is 3, I have n minus 4 cases. So I can generalize this. You can do the same thing for 2 and 3. I can generalize this. Here is what I'm going to do. I'm going to write 2 summations, and this is going to give me this generalized rule for this thought process. Okay, let me use LaTeX format for this. Just be patient, and then I'm just going to type this. So I'm going to use 2 summations, and I'm going to tell you what they mean. Okay, in a moment. Hopefully this will work. Okay, so what is happening here? N is number of the cards. So J is the numbers at the end, okay, and I is the numbers at the beginning. All right. So if the first number is 1, and then if the second number is, if the first number is 2, and then if the first number is 3, so I is counting the first numbers, J is counting the second numbers, and this is number of cases when the first number is I and second number is j. So I got this generalized rule from this thought process. Let me not get into details of this. I'm leaving it to you, so you can a little bit spend some time to understand how we can connect this thought process to this equation. Let us do a very simple coding exercise for this mathematical equation and see if we can get the same result that we got earlier. Okay, and then maybe we can think about what Rupa earlier said. Let me see if I have any. Yeah, there is no link for the notebook, so I'm just there is nothing. So we're just typing everything from scratch as we think and then try to solve the problem. So let us write the code for this. So let me see. Let's say there is n is sorry. So what is it? N is number of cards. So here it's 600. Okay. And then let's say k is how many cards we are going to pick minus 1. Okay. So I'm going to pick, if I'm going to pick 2 cards, k is 2. If I'm going to pick 3 cards, k is 2. Okay. And then the summation, the SS is summing up the number of cases where it satisfies x1 less than x2 less than x3. Okay. Now let's write for I in range. I'm just writing the code for this guy here. Okay. For I in range n minus 2. So instead of 2, I'm using k. Okay. N minus k. So I'm writing a more general formula. Here 2 is because I'm picking 3 cards. What if I pick 4 cards? Then instead of 2, I'm going to use 3. Okay, so that's why I'm using k. Okay, all right. And then for j in range what is it? N minus k minus I. Okay. So S is going to be equal to N minus I minus J. Okay, so let's see if this is going to work. Okay, it worked, but we don't know if it worked correctly or not. I think it worked correctly, but let's see for 600 cards and the number of cases where we have x1 less than x2 less than x3 is this many. Okay, all right. So the second component of the problem is now we found number of cases which satisfy the condition. The second component is we have to find total number of cases, the total number of cases. So if we are talking about without replacement, then what we have to do is we need to use factorial, right? Import math. And so 5 times 4 times 3, right? So if there are 5 cards, total number of different cases is when you pick 3 cards without replacement is 5 times 4 times 3, right? So this is basically what is it? 5 factorial divided by 2 factorial, right? So let's write it. So this is total cases is math dot factorial. So number of cards n divided by math dot factorial n minus k minus 1. Okay, if we are picking 3 cards, k plus 1 is number of cards we are picking, so n minus number of cards, right? So this is the total number of cases. Okay, and then let's see what is print s divided by total. Okay, it's going to work. So it's 0.1683. Let's go all the way back. It's very close to what we found with the simulation. Okay, again, we just use some thought process here to see if we can have some general formula for number of cases where this condition is satisfied. Once we found number of cases that satisfy, then we divide total number of satisfied cases by total number of all cases. So this is for without replacement. Now, I was thinking without or with replacement total number of cases which satisfy this condition may not change. But Rupa is saying that they are different because they can be smaller or bigger than each other, hence the number will change. So with, again, I'm talking about with replacements. Let's think about it. And then I'm going to move to the next question. Okay, let's think about it. X1 less than X2 less than X3. You are picking cards from a deck of cards, and this time you are replacing the cards. So you pick the card and put it back. Let's say you picked card 3, okay? And second case, let's say you picked 4, okay? Now you put 3 and 4 back, right? So if you pick 3 and 4 again, is it going to satisfy this condition? Right? If you, let's say, look, you pick a number, okay, 3, okay? Now, to satisfy the condition where X1 is less than X2 less than X3, the second number has to be bigger than 3. So it cannot be 3 itself. You cannot just pick 3 again. So the only difference between with and without replacement is you can randomly sample the same card again. But sampling 3 one more time is just simply is not going to satisfy the condition. So you have to pick a number different than 3 and bigger than 3. Okay, all right. So it's, let's say you picked 4. Again, the third number has to be different than 3 and 4, because if it is 3, again, the condition is not satisfied. If it is 4, again, the condition is not satisfied. So it has to be different than 3. And as long as these 3 numbers are different from each other, I mean, the total number of cases satisfying this condition with or without replacement is not going to be different. Okay, if that is the case, let's go back to our example here. The total, let's call this total 1. So then total number of cases for with replacement will be different, right? Total number of cases with replacement is actually n to the power of what is it? N to the power of k plus 1, total number of cards. Again, remember, k is total number of cards minus 1. Okay, so that is the total 2. Then let's let me run this. This is total 1. Let me just simply put it here. And then this is total 2, okay? So again, as you see, for large number of cards, these results are, mathematical results is almost the same. But if I reduce number of cards, the reason why for large number of cards the result is almost the same is because for large n, the factorial, this total 1 and total 2 are very close to each other. So they are really large numbers. Okay, in that case, because the denominators are really large numbers, it's not going to make too much of a change. If it is 60, I'm expecting that it's going to make some change. Yeah, when you reduce number of cards, as you see, the results for these 2 cases will be different. Okay. All right, let me stop here for the first question. Let me go to the next one. Okay, again, I think we're not going to have enough time for the third one. Maybe we're going to have another session for the third question. Okay, the next question is a little bit, I think, a little bit more difficult than the first one. Let's read the next question. So you are given a fair coin and you flip the coin, okay, until either heads, tail, or heads, tail appears. So what's happening is you flip the coins, right? So you can flip the coin in any order. So for example, it can all come H. Every time you flip the coin, it can come head, right? So this is a very less likely thing to happen, but it happens. So what we are looking for is a sequence of 3 flips, okay, which is either, for example, if I flip T, right, then HHT is satisfied, I stop, right? Or let's say HH, yeah, as you see, HHT is said, for me to get to HTT, I need to put one more T, but here I don't have to put the second T because already the first case is satisfied. Now you got the feeling that one more likely to appear first. You got some feeling, right? So it will be much easier than mathematically solving this problem. And then we'll try our best to solve it mathematically. All right. How can we solve this problem with simulation? Again, it's a very simple, actually code. So let's see. So I'm going to use uniform distribution from, you can write the code in a different way. I'm repeating stats. I will import uniform distribution. So what happens is the way you can simulate a coin flip, right? So when you flip the coin, it's half probability with 1/2 probability, it is tail, 1/2 probability, it is head, right? So how can you simulate this? What you're going to do is you're going to pick a random number from a uniform distribution between 0 and 1, okay? Between 0 and 1. If the number you pick between 0 and 1 is less than 0.5, then you can assign it to head. If greater than 0.5, you can assign it to tail. Because between 0 and 1, right in the middle, 0.5, right? So from 0 to 0.5, from 0.5 to 1, the probability that we can pick a number before 0.5 or after 0.5 is the same. In other words, so between 0 and 1, you slice it from the middle. So what you have is 0 to 0.5 or 0.5 to 1 is each side has a probability of 1/2. So that's what we are using here to simulate. That's why I'm using uniform distribution here to simulate flipping a coin. Okay, so I'm going to repeat an experiment many times. So at each experiment, the moment I have one of these HHT or HTT, I'm going to stop. But until I get in an experiment, until I get HHT or HTT, I will keep flipping the coin. Okay, that is my approach. So I'm going to run this experiment for a number of times. So I am going to keep H counts and tail counts. Okay, every time, let's call it this head has tail, HHT count. Let's make this HT count, and let's make this HTT count. Okay, HHT count and HTT count, they both are 0. That's what I'm going to be incrementing each time one of these guys appear in the sequence. Okay, all right. So what I'm going to do is I'm going to keep the tail or head characters in a string. So that string, let me initiate it as a 0 empty string. Okay, and then I'm going to repeat this experiment. I used I before. A number of times. Okay, how many times? Let's repeat this experiment. I don't know, 10,000 times for now. You can increase the number if you like. It's not going to change anything. Okay, so now inside the for loop at this iteration, I'm talking about a single experiment. Okay, this is one experiment. At each iteration, I'm going to repeat this experiment. So what is the experiment? I'm going to keep flipping the coin until I get either HHT or HTT. Thank you, Alexa. I just saw here. Yeah, you can also do random choose 0, 1, 1. You can also choose random int 0 and 1, Jeffrey. Thank you. So you can, as I said, you can use different ways. I like using uniform distribution because it gives me more flexibility. So I can simulate what is the probability 0.3 and 0.7. So I can change the P and Q values for binomial distribution, right? So that's why I prefer using uniform distribution. Michael is asking, can we think about the coin analysis from an entropy perspective? Which message has lower entropy? Wow, Michael, you are talking about information theory here. Let's not get into it. Let's not get into it. Okay. Yeah, you can use entropy to answer the question. Again, the one which appears the most is going to have a higher probability. For higher probability, if you use equal number of characters, the one with less probability with higher characters will have, I think, a higher entropy. Do you worry about float comparison with uniform distribution? Do you worry about float comparison precision? At this point, I'm not worried about that at this point, Michael. Okay. So let's see. I'm going to repeat this experiment many times. Let's talk about the first experiment. Let's see the first experiment, the flip. Let's call this a flip. Thank you, Michael. Flip. I'm going to create just sample from uniform distribution. Okay, flip will be just one value between 0 and 1. Okay. Now, a character is going to be either H, or if the flip is greater than 0.5, okay, or T. Okay, so it's going to be either character H if flip is 0. You can change this. You can make this T and this H. It doesn't matter. Okay, and then you're just going to add this, okay, to the string. Okay, you can say. So this empty string is going to get populated with H and T. So again, they are flipping the coin. H, I'm going to put it aside. T, I'm going to put T next to H. So each time I flip a coin, it's going to be, what is it? It's going to be added into, what is it? This string. Of course, I have to stop somewhere, right, during the experiment. So I'm going to repeat this process. I try to solve the problem in the different way than what I have in mind. So let me initialize my string for each experiment. So we're going to solve this problem in a different way too. Let's be patient. So at each iteration, at each experiment, I start with an empty string, okay? And then there is some condition. As long as that condition is there, okay, I'm going to keep flipping my coins, all right? So as long as some condition is true, I'll keep flipping my coins. So when that condition is not set, when this true is turned into false, I'm going to finish that experiment, go to the next one, okay? Start the next one. When I start the next one, again, this string is going to be an empty string. All right. So I keep adding. So here, what you have is inside this for loop and while loop, as long as you are inside the while loop, you keep flipping the coin, and this is what's happening. H, 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 T, 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 H, H, T, T. So as long as you have H, T, oh, I got the H, T, T. H, okay, H, oh, I already got T. Okay, so as long as you don't have any of these two, you keep flipping the coin, and ST is going to get populated with H and T, but you don't see HHT or HTT sequence within this string. Okay, so the moment you see that string, that sequence in the string, you're just going to break the while loop, right? So every time we need to check the last three characters of the string, because the last three because the first time HHT or HTT appears, we are going to stop, right? In that case, we need to check the last three of the string every time. Okay. Then what we're going to do is, G is the last three characters of my string. Okay, again, my string is getting fatter and fatter with each flip, and I'm always checking the last three characters. If the last three characters, now let's add the if statements. If my last three characters is either this HHT, okay, if it is HHT, then HHT, I'm just going to increment this. All right. So let's do the same thing for the next case. Aleph. G is HTT. This time HTT is going to get incremented by 1. So I'm just counting number of times my experiment is giving me either HHT or HTT the first. So whichever comes first, I will stop the experiment, and then I'm just going to increment one of these variables. Okay. All right. I think this is almost done. So let's print. Okay. What is that? HHTC or M? HTTC. This else. It's not going to change it, but let's add this one too. So once you increment, you need to break the loop. So once I increment, I need to break the loop. So let's break the loop. Okay, thank you, Jeffrey. Yes. So that means once I increment, I'm done with this experiment. I break this while loop. I go back to my for loop. Okay. Yeah. Thank you. Yes. I think now it should work. Let's see. Yeah. So as you see, HHT has almost twice the likelihood probability than HTT happening the first time. So again, each time I'm flipping the coin, I'm just observing the last three flips. The moment I got HHT or HTT, I just stop for that experiment. Okay, it's say 0.668 or 0.33. So it's like 2.2/3 and 1/3. Okay, I think this is a good enough answer. So let's try to solve this problem together using a little bit of mathematics. And this part will be a little bit tricky, okay? But let's, I know it's almost 1 hour now. I'm gonna take maybe 5 more minutes of your time and then I'll be done, okay? So the next question, we can work on it in our next meeting. All right, so let me also go with my notes. So let's think about this problem, how we can solve this problem. And let me see if there are any questions. All right. So please let me know if you have any questions or corrections. I'll be happy to check it for you. So let's say, and by the way, if I start with T, it's not going to change anything, but let's say, let's assume that I start with H. Okay, I start with H, and then the next, this is the first one. So the next one can be either H or T, right? So if it is H, then the probability is 0.5. If it is T, then the probability is 0.5. Okay, and then by the way, let me write the characters that I'm looking for, HHT or HTT. This is what I'm looking for. Okay. So it's either HH or HT, right? And both have 0.5, what is that, probability. Now, I'm assuming that I start with H. So if you start with, so if you also consider the probability of the first character being H or T, you need to multiply this by 0.5. At the end, you will see it's not going to change the result. Okay, now let me go with HH for a while. Okay, let me go with HH for a while. So if the second one is H, then the third character can be H with a probability of 0.5 times 0.5. Or it can be HHT with a probability of 0.5 times 0.5. All right. So now this is the condition which is satisfied. Okay, very good. Satisfied. Okay, so that means we have one case where the condition is satisfied. That case is with probability 0.25. All right. Okay, but then if it is HHH, let's go with HHH. Okay, look, I started with H, then let's go step by step. I started with H, then I checked HH, and then I checked HHH, and now I'm going to focus on HHH, because if that is the case, I'm still flipping the coin. HHH. So there are 3 flips, and I still have, I still did not get what I'm looking for. Now, the 4th one can be either H, this time with probability, with, 0.5 times 0.5 times 0.5. Or it can be HHHT, right? With probability, again, 0.5 times 0.5 times 0.5. All right. Do you see anything here? Do you see something is happening here, right? Can you see that? Can you see any, something is going on here, right? So I keep repeating the experiment. Let's say I started with HH, then if it is HHH, so in this case, I can continue doing this. HHHH. Again, if the 5th one is H, this is the probability with, this time I'm going to copy this, times 0.5, okay? Or it can be again, this probability. Look, here it is satisfied. Here it is satisfied. So how many, look at this, this is satisfied, this is satisfied. So it's almost like there is, it's almost like geometrical, right? So I'm every time I have an H in the next one I'm hoping that it's going to be a T. So I'm talking about this case. If all my previous 2 cases are H, I'm hoping that the 3rd one is T. If the 3rd one is also H, again, I have 2 H's already accumulated. Now I'm looking for the next one. I hope it's going to be a T. So if you look at these probabilities, 0.5 times 0.5, 0.5 times 0.5 times 0.5, let me just add these probabilities, these probabilities, okay, which is giving me the satisfied condition. Actually, there is something called, I don't know if you guys, I'm pretty sure you guys dealt with, let me write first this way, 1 plus, what is it, 1 over 2, let me use 1 over 2 plus, it's going to be better, 1 over 2 to the square of, it's 1 over 2 squared, okay, plus 1 over 2 cubed, plus blah, blah, blah. It's going to the infinite. So is anyone who knows the geometric series? Anyone who knows the answer for this one? If this number is, what is it, 1 plus x squared plus x cubed plus, if x is a number less than 1, do you remember any formula for this one? Will it be 1 over 1 minus x? Anyone remembers this? Right? That is the case, right? So if we have a geometric series where x is, every time we're taking the, increasing the power, and x is, I think this is called geometric expansion. If x is less than 1, then this summation, which is going to infinity, it is at the end, if you take the limit of that, it is 1 over 1 minus x. So this is what's happening here. What's happening here? Actually, what's happening here is this here. Okay, so let me just keep the first 1 over 2 aside. It's 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the power of 4. So eventually, this is going to be 1 over 1 minus 1 over 2, which is going to be equal to what? 2. Okay, but this has to be multiplied by 0.5, okay? This has to be multiplied by 0.5. So what I'm doing here is, what I'm trying to do here is, I'm calculating the components of this probability. The first one is, there is a 0.25 probability that I'm going to, what is it? I'm going to get HHT. And then there is another probability where I'm going to get HHT as a result of this geometric expansion, okay? And the geometric expansion has a probability of 1, but to initiate the geometric expansion, I need to have HHH first, okay? Which is a probability of 0.25. So I'm multiplying this by the probability coming from geometric expansion. The summation of that geometric expansion is 1, okay, plus, okay. So this is the second component. Any questions up to this point? I know it is a little bit, now it's a little bit complicated. Any questions up to this point before I talk about the third component? Again, please remember, I started with H, and I included the second one, H. It has a probability of 0.5. And I included the third one, it has a probability of 0.25, okay? HHH has a probability of 0.25, right? And then the fourth one is H. Every time I have 2 H's, then I will always look forward to the next one. If it is T, then the condition will be satisfied, okay? So as long as I get the next one as H, as long as I have all H's, I will always look for the next one, hoping that the next one will be T. So that next one, hoping that next one will be T, next one will be T, it's forming a geometric expansion, and that summation is equal to 2. The probability that we have that geometric expansion starting is 0.25. Geometric expansion is 2, but I have to multiply this 1 over 2. So let me, it's actually 1 over 2 times 2, because here I have 1 over 2. I need to, let me write this way more explicitly. This is 1 over 2 in parentheses, 1 plus 1 over 2 plus 1 over 2 to the power of 2, okay? That is equal to 1 over 1 minus 1 over 2 times 1 over 2, which is 1 over 2 times 2, which is 1. Okay. So this geometric expansion has a probability of 0.25. This is the second component. Now let's think a little bit more. Okay, let's think a little bit more. Let's think a little bit more about if we have any third component for this probability. Can you think of any third component here? Any third option for HHT? So first we have H. If it is HH, we are hoping that the next one is T. Okay. If it is HT, then we skip this part. We skip this part. Now, if it is HT, it will be either HTT with probability 0.25. Okay. Or it's going to be HTH with probability 0.25. Okay. This last case is interesting. Last case. If it is HTH, they are actually going back to this case here. If HTH, they are going back to the very beginning again, because the last one is H. The first two are actually useless. The last one is H. Then I'm hoping that the next one is going to be H or T, right? So I'm starting over. Right? In other words, whatever this whole process is, let's call it T. The probability of this whole process is P. The moment I got HTH, I'm going back to the entire process one more time. So what I'm going to do is, the probability that I'm going to get HTH is 0.25. Okay. And the moment I hit HTH, I will go back to and begin with the entire process one more time. So let's say the entire process has a probability of P. When I say entire process, the probability of receiving HHT. Okay, that's what we are looking at. So the summation of these three will be equal to P. Okay, let's pause here for a while and then think about what we did. Okay, I feel like there's a Markov chain. Yeah, Michael. So, so we are just using. I mean, right now we are navigating our way, okay, to find a solution with some rough approach. Let's call it that way. Okay. So what I want to do is I want to find a way to represent this probability of getting HHT when I flip a coin one after another. Okay, each time it's either H or T. So what I did is I'm just considering multiple cases. The first one is, let's start with H. So I flip the coin, it is H. Then I need to see what is the next one going to be. It's either HH or HT. If it is HH, then I keep flipping the coin, because if it is HH, there is a hope that the third one is going to be T. And that's what I looked for in here. Okay, that's what I look. So the moment the first one is H, I am initiating a process for finding HHT. But if the second one is T and the third one is H, I'm going back to this process where I initiated at the very beginning. So that's why I said the moment I hit HTH, it's an interesting case, because I'm going back to the process of finding the probability for HHT. So this entire thing, the probability of HHT is P, okay? And P is actually summation of three different cases. First, I just plainly get HHT by three flips, okay? The first one is H, the next two flips HT, that is HHT. The second case, I keep getting HHH. In that case, I will always look forward to the next one if it is going to be T or not. Okay, that is geometric expansion, which we found the answer for it. Okay, so HHH is probability of 0.25, and following HHH, the entire thing has summation is 1. So this is the second component. Okay, and there is a third component where I get this HTH. The moment I hit HTH, I'm going back to where I started from. Okay, that's why the point where I started from has the probability of 20.25, and where I started at, the probability that I'm trying to find is P. Okay, so now I can solve this equation for P and find the probability that I'm going to get HHT. Let me get in questions, or the whole process will be the same if we started with T. If you started with T, yeah, what you're going to do is you're going to multiply this by 1/2. And then you're going to multiply this by 1/2. Because the probability that you're going to get T is 1/2. But then you need to expect the second one is going to be T. So the H, I'm sorry. Then you need to multiply both sides of the equation by 1/2. It's not going to change anything. So if you solve this equation for P, P will be equal to 2/3. You can try it. All right. So let's call this P1. I'm going to stop, guys. P1. Now, let's find the same question for HTT. HTT is much simpler. HTT is much simpler. So again, let's begin with H. If the second one is T, and if the third one is also T, then we got. So this is condition satisfied. So condition for HTT is 0.25. All right. But HT, if the third one is H, again, I'm going back to the beginning. So again, 0.25 times going back to the beginning. Okay, this is P2. If you solve this problem for P2, then P2 will be equal to 1/3. Okay, let me stop here. I think you guys already got tired, right? And again, the solution for this one was not so. I tried my best to explain it, but the mathematical solution is not so Maybe I should draw it. I think drawing might be more helpful. Yeah, thank you, Michael. And I think the simulation was much simpler, right? Simulation was much simpler. You can try different versions of the simulation. You can get the same results. I have different versions actually myself tried. You can get the similar result. Okay, thank you for listening. And I'm going to see you guys in our next meeting for Statistics 5. I'll add a couple of more questions in addition to this one. Okay, thank you for listening, and let me know if you have any questions. No, okay, thank you. Take care. Bye.